I would like to discuss how Gauss's law can be used to deduce some deep truths about how conductors behave. A conductor is something like a metal. So here I have a conducting object, a piece of metal which I have taken a slice with a hacksaw so you can see through it. It's got a cavity inside, and this shading means it's got metal. Now, first of all, a fact of life is that in conditions known as electrostatic equilibrium, which I'll abbreviate as EE, electrostatic equilibrium, charges are not moving. That's the meaning of equilibrium. The net force on a charge is zero. Under conditions of electrostatic equilibrium, you cannot have any electric field inside the metal. If you had an electric field inside the metal, then by F equals QE and QE equals MA, you will get an acceleration. So if you have an electric field, you will get an electric force. If you have an electric force, you will get an electric result of that would be an acceleration, and then you're no longer under conditions of electrostatic equilibrium where the acceleration has to be zero. So just by semantics or just verbal arguments, we can say the electric field inside a metal has to be zero. So that's the first result. That's the sort of the zeroth result. E inside metal equals zero. That is something that we always assume. Now, when I say inside the metal, I don't mean here. I don't mean in the cavity. I mean in the portions where I have shaded it. Once you accept that the electric field inside the metal is zero, under conditions of electrostatic equilibrium, you can prove two very important results. And that is, also, these are results which are very useful in real life. So sometimes people wonder what's the safest place in an electrical storm. If you're in a big thunderstorm, what's the safest place? And the answer is, it's inside your car. So if your car is a hulk of metal, by the way, this does not apply if your car is not made of metal. If it's one of those newfangled cars made of plastic, it won't work. But if it's a traditional metal car and you're inside the car, you're pretty safe. That's what number one proves. If you have a lightning strike that comes and zaps your car, all the charge will reside on the outer surface. None of it will come and affect you inside. The second statement is interesting. It says that you cannot have a secret lab. So if you have if you try to build a lab deep in the mountains, okay, and you surround it with a metal bunker with thick metal and all that, and you start manufacturing a charge, a drone flying above your lab can find out that you're doing it, because whatever charge you make inside will end up escaping outside. So these are the two important theorems. The first one's practical application is that you'll be safe in a thunderstorm inside a metallic object, and the second, by the way, the metallic object in part one is sometimes called a Faraday cage, and for part two, you cannot secretly, without government knowledge, make charge in a lab. That's the practical application of part two. How can we prove these two tremendous results? It seems like these are magic, right? So both of these results can actually be proved using Gauss's law. Suppose I put a charge Q in this conductor. I will show that all that charge Q that I put on this conductor must reside on the outer surface as follows. I'm going to choose a Gaussian surface S here. And I'm going to use Gauss's law. Well, if you remember, Gauss's law says that the closed electric flux, the oriented double integral of E dot dA, well, inside the metal, wherever the Gaussian surface is, inside the metal, the electric field is zero. So I'll put a zero through the electric field vector, and so the flux is zero. If the flux is zero, that means the enclosed charge is zero. because the flux is also equal to the enclosed charge by epsilon. Now what I'm going to do is I'm going to take the surface to approach the outer surface. I make the surface bigger and bigger and bigger, and so in doing that I've shown that all this charge has to be on the outer surface and not anywhere else. It's a beautiful proof. How do you prove the second statement? If you have a cavity charge, it will escape outside. And when it escapes outside, it becomes what's called an induced charge. Okay, let's prove this in the same figure. I'm going to put a cavity charge Q. Now imagine I don't have that, okay? For now I'm going to put my finger over that. So there's no lightning, that's lightning charge, that's not there. So I put a cavity charge there. What does Gauss's law tell me about this situation? Well, once again, I'm going to write the left hand side of Gauss's law, and it's going to be 0 because there is still no electric field on the Gaussian surface S. So I'm going to get 0 equals to the enclosed charge over epsilon naught. Well, that looks like a massively wrong statement because the enclosed charge is not 0. There's definitely a Q because I put it there. I know there is a Q because I put it there. So Q enclosed cannot be 0. Therefore, how can we reconcile the statement that 0 equals Q enclosed and the fact that Q is sitting right there? There has to be a charge induced on the inner surface equal to minus Q. That is the inescapable conclusion. Therefore, minus Q must be induced on the inner surface. However, this metallic portion was neutral to begin with. I had not blessed it with any charge. So if it's got minus Q inside, it should have plus Q outside. Plus Q must be induced on the outer surface because the metal as a whole is neutral. In this amazing fashion, the charge Q in the cavity has escaped outside. Okay, if what charge Q did was it induced a charge minus Q to satisfy Gauss. And how does that minus Q develop in the first place? The minus Q develops with some electrons gathering there. If electrons gathered there, they had to have come from somewhere. Well, they came from there. And so you have some starving atoms here with a positive charge because they have lost their electrons. And that's the story of Gauss's law for conductors. We can use this in traditional Gauss law problems. So I want to take a simple example of Gauss's law and show you how this is done. This is a pretty famous example. It's called a coax cable. Coax cables are usually used with currents, but you can also use them with static voltages, especially in undersea cables, because static can occur at the same time as other kinds of mobile currents. So I'm going to pick an example where I have, just for the sake of simplicity, I'll take this to be an infinite core wire of constant density lambda naught, and I'll surround it by a shell, a coaxial shell. You can think of this as infinite, so I'm just drawing a small portion of it. And the coaxial shell, I put a charge density sigma naught on it, on its outer surface. Okay, and this shell is metallic. For the sake of drawing, let's assume that sigma naught is bigger than 0 and that lambda naught is bigger than 0 also. And I'm not telling you any relationship between lambda naught and sigma naught. They're just two arbitrary quantities. I want to find the electric field everywhere. Well, you proceed as usual. You use the Gaussian surface on this side around the core, and look at my previous video for the cylindrical symmetry. The left hand side of Gauss's law is going to be, so this is Gaussian surface S1, and we'll also pick a Gaussian surface S2 that's out here. So for the Gaussian surface S1, the left hand side, using the cylindrical symmetry arguments laid out in the previous video, will end up being the electric field as a function of radius times 2 pi r times L will be equal to the charge enclosed, lambda naught L over epsilon naught. The little l's cancel out, and I get the electric field R equals lambda naught over 2 pi r epsilon naught. Now let's put some dimensions on these on this coaxial shell. I'll say the inner diameter is A and the outer diameter is B. So this is the expression that's valid for 0 less than r less than A. Well, what about between A and B? Between A and B, the electric field is identically 0 because it's metal. So I'll write that here. Now whatever charge density I give the surface should be on the outer surface because of the first principle. All charge resides on the outer surface. So the sigma naught will only be on the outer surface. It will not be on the inner surface. So I only have to worry about sigma naught on the outer surface of the Gaussian surface when I consider the charge enclosed by the Gaussian surface S2. So for the Gaussian surface S2, the left hand side of Gauss's law is the same and the right hand side changes. So let's write what it is. On the left hand side, I have the same by the cylindrical symmetry arguments. On the right hand side, I have enclosed this part, which is lambda naught L, plus I also have enclosed sigma naught times the area of the outer surface, and that's going to be sigma naught times 2 pi B times L, because the outer surface is got circumference 2 pi B and length L. That whole thing divided by epsilon naught. Once again, the L's cancel out, and I'm going to get the electric field as a function of radius is equal to lambda naught divided by plus 2 pi B sigma naught divided by 2 pi r epsilon naught. If you'll notice, the sigma naught here has got units of coulombs per meter squared, lambda naught as units coulomb per meter. Let's make sure the units work out here. That's coulombs per meter. That's coulombs per meter squared times meters. So this whole thing is still coulombs per meter. So the units do work out. Lastly, the story is not finished until we are able to produce a plot of the electric field. So let's do that as a final step in this problem. I go from 0, which is the middle part, and then all the way up to A, and then to B, and then out to infinity. What do I get? First of all, between close to 0, it's going to be infinite. So I can't even draw the field. I have to be careful. I'll draw some dotted lines. That's the electric field at A. At A, it experiences a jump discontinuity. Now, in more advanced classes, you'll find out that this is not what happens. There's some exponential factor here called the skin depth. But in the class we have, UP1 is a very simple class compared to the real life. So what we're going to do, because sigma naught is bigger than 0 and lambda naught is bigger than 0, this whole thing is going to be bigger than lambda naught. So if it had nothing more than lambda naught, it would have decayed and gone its merry way like that. But now it's getting a boost. So another jump discontinuity, and then it decays again as 1 over r. So that's the full electric field profile. And the jump discontinuities, to emphasize, don't really exist in real life.